Right, so today's lesson is Unit 2, Lesson 3 on inertia. It's Newton's first law of motion. But it didn't start with Newton, it started with Galileo. So Galileo sort of did a thought experiment. Well, actually, let's trace it back even further to Aristotle. So Aristotle said that in order to keep something moving, it required a force. Not a bad idea. But you're ignoring friction in that case. Okay, Galileo tried to sort of remove friction from the problem. Now, he couldn't actually do it, so he had to create a thought experiment because friction, it's everywhere. You can't get rid of friction. So in order to do this thought experiment, he imagined this half pipe here. And if you put a ball at a certain height, the ball would go down the half pipe. Now, if there was friction, it wouldn't make it quite up to the top. But ignoring friction, in an ideal world with no friction, it would come right back up to the same height. And this is true even if you were to, say, alter the half pipe so that the right half wasn't as steep and sort of did this. In that case, it has further to travel, but the ball would still come back to that same height. There we go. Then he took it one step further and imagined, okay, well, what if the other half of that half pipe doesn't come up at all? What if it keeps going horizontal forever? In that case, he thought of the idea that it would forever be trying to reach that height, but would never be able to reach it, meaning it would keep moving forever. So this shows what Aristotle thought to be wrong. A force is not required to maintain motion, because in this case, the ball would be rolling forever with no forces acting on it. So he came up with the idea that, nope, a ball with no force on it will keep its state of motion. And Newton used this idea in his first law of motion, and he called this property that all matter has inertia. Now, inertia is that tendency to want to keep your state of motion. So his first law says, an object at rest or in uniform motion means constant velocity, will remain at rest or in uniform motion unless acted upon by an external unbalanced force. So that means if you're at rest, you tend to want to stay at rest unless a force acts on you. And it's important that it's unbalanced force as well. Right? If you're just standing here and one person pushes me from this side and the other person pushes me from that side, if they're pushing with the same force, well, then I'm not going to change my motion either. Right? So it has to be an unbalanced net force. Right? And it also has to be external. Right? I can't stand here and try to push myself and have my whole body move across the room by doing that. Otherwise, I could just lift up on my feet and go flying. That's not going to happen. So let's look at a couple examples. So I have an example here. Here you have a cart with a whole bunch of marbles in it, and it rolls down the ramp. Now, if we put a little block here, the cart hits the block, and so the block exerts a force on the cart, and so the cart stops. But the marbles are also moving down the ramp, and that block does not put a force on the marbles, and so the marbles will still move forward. They want to keep that same state of motion unless a force acts on them. So they'll keep moving forward until they hit something. This is a very important idea, especially if you are in a car. So let's say you're in the highway, you're driving at 100 kilometers per hour. Yes, your car is going at 100 kilometers per hour, but the important thing is that you are going 100 kilometers per hour. So if something were to exert a force on your car to bring it to a stop, you would keep going at 100 kilometers per hour until something exerted a force on you. And this is car safety, right? What would you prefer to exert that force on you? A seatbelt and an airbag, or a windshield and the pavement? Right? I think it's an easy choice to make. Here's another idea with inertia. This is a seriously scaled down idea of the tablecloth with a whole meal setting on top of a table, and you sort of whip the tablecloth underneath. Same idea, but this one you can do at home without, breaking all of your parents' dishes and glasses. You can just take a cup, you can fill it halfway with water, and then take a rigid piece of paper, not like a regular piece of paper, but maybe like a cardstock, or like cue cards, or a little piece of cardboard that you can cut out from a box. And then you place a quarter or a loonie on top. And if you flick the piece of paper perfectly horizontal, the piece of paper will move and the quarter will drop. Okay, it wanted to stay where it was. It's in a state of rest, and if there's no force acting on it, well, then the card will just slide underneath. And then, of course, gravity is acting on it at this point as an unbalanced force, so then it will drop. So this is the idea of inertia. So let me pause there. Let me see if you guys can think of or tell me any examples that you know of inertia. So a couple of things that I wanted to mention, and especially in some of the examples that we've done, is that inertia wants you to, it's a tendency to maintain your state of motion. And that's not necessarily related to speed, but velocity. And velocity is a vector. So if you change the magnitude of velocity, yes, again, inertia wants you to maintain that state of motion. But in this example, where you turn right in your car, if you maintain the same speed, you still feel like you're being pushed out to the left because your body wants to stay to the left. So there's a directional component to this as well. So I have this last point here. If the velocity of an object is changing in either magnitude or direction, or both, the change will be caused by an unbalanced external force. Okay, and of course, you want to maintain your state of motion in that case. So when you turn right, you feel like you're being pushed left, but you're not. You're just going straight, and your car is pulling you to the right. There are lots of other cases. Like this is a big one. This is how they landed the Spirit rover on Mars a long time ago. And I can show you a video on how they also landed Curiosity, and recently they landed Perseverance, which is a really, really difficult task to do because you have something moving extremely fast and it's going to want to keep moving extremely fast, right, until it hits something like the surface of Mars. But you don't want it to hit the surface of Mars moving that fast. So you need to do a lot of work to actually change its state of motion. Apply lots of smaller forces on it over longer periods of time so that it doesn't just make a huge crater on the surface of Mars. And I'll show you a video of that as well.